Welcome to a session titled as Harnessing Emerging Data Plane Technologies for Next Generation of Load Balancers. I am Shatakshi Mishra, working as a senior software engineer in Marvell. I have 3+ years of experience in implementing programmable data plane using P4 and optimizing data path offloading for cloud-native solutions like CNI, service mesh, and load balancers. So in this talk, we're going to focus on two main aspects that are load balancers and the data plane technologies that are used behind them. Over time, load balancers have evolved significantly from just distributing workloads across backend servers to supporting a wide range of advanced features that ensure seamless application delivery. Now, the wide range of advanced features we just talk about are like load balancers can support layer 4, layer 7, and DNS-based load balancing. They can act as reverse proxy as well. They support security features like SSL offloading, TLS termination, MTLS, and DDoS protection. They can do health checks and monitoring. They can scale automatically according to the dynamic change in environment. And integrated certificate management systems are also present in the current load balancers. And also they can maintain user information for a particular session. So are load balancers truly that important? Absolutely. And that's why there's a wide array of solutions that are available in the market, like Nginx Plus, HA, proxy load balancers, Camp Load Master, and there is a long list of those. All these support subset of features that we just talked about in the previous slide. Now, data plane technologies serve as the backbone of these solutions, enabling them to support a multitude of features that we just now discussed. Some of these solutions are open source, some are proprietary. So now in the upcoming slides, we're going to talk about the open source data plane solutions that are being used widely behind these load balancers. Broadly speaking, eBPF is the one that is used mostly. Some of the high-performing load balancers are also using DPDK, and very few, but are still using VPP. So load balancers like Loxi, Unimog, Cilium, Catran, they are using eBPF with XDP hook to perform load balancing logic at the device driver layer. So you can perform load balancing at the device driver layer and can take all the actions and decisions on that layer itself without sending traffic to the kernel. Then comes the VPP-based solution. So high-density scalable load balancer and VPP's own load balancing plugin allows us to perform load balancing logic at the user space. Now, inward proxy, which is being used widely as for layer 7 load balancing. Yeah, inward proxy, which is being used widely for layer 7 load balancing in many of the open source projects, also support VPP networking stack. And Alibaba Cloud Server Load Balancer use DPDK, and load balancers like F5, Citrix, 8 and Thunder, in their ADC models, they support DPDK for fast packet I/O. So yeah, we will going to talk in detail about these three. First, we'll get to know what are data planes. So in networking, data plane, or also known as forwarding plane, is the part of the network which carries or handles the actual user traffic. DPDK, Data Plane Development Kit. That's a high-performance user space packet processing framework, mostly used for packet I/O. It bypasses the kernel networking stack and allows you to send your traffic directly to the user space. eBPF, Extended Berkeley Packet Filter, a powerful in-kernel packet processing engine which allows custom processing inside the kernel. And then VPP, which is Vector Packet Processor, a high-speed modular open source software network stack that helps in performing efficient packet processing inside the user space. So yeah, some more detail about all three of them. DPDK reduces latency by bypassing the kernel layer. Continuous packet polling via DPDK provided poll mode drivers, where CPU continuously poll NIC for incoming traffic instead of relying on the interrupts. DPDK also optimizes memory with large pages and pools with the help of huge pages. DPDK offers libraries and drivers for secure communication and cryptographic operations, and it allows NIC to DMA packets directly to application address space. Then comes the eBPF, which allows you, which actually runs in a secure kernel environment, allows you to run custom eBPF program on demand inside the kernel. eBPF programs get triggered in response to network events or system calls. JIT compiler is being used to convert eBPF bytecode to native machine code. And eBPF is being used widely with XDP hook, which allows us to launch a BPF program as soon as packet is hit on the net interface. Then comes the VPP, which is a universal data plane that supports L2 to L4 networking, runs in user space, and can be deployed on virtual machines, bare metal containers. VPP is based on a graph-based architecture for packet processing. That's why it's also like a kind of pluggable architecture. You can add or delete functionality with the help of graph nodes. And it also offers fast lookup tables optimized for quick data retrieval. VPP has been enhanced through the extensive use of plugins, and DPDK is also one of the example of those kind of plugins. So these two diagrams effectively illustrate the working mechanism of the data plane model we just discussed, providing a clear comparison of their architecture and workflow. And we're going to discuss them on the basis of how load balancing can be done with the help of them. So first comes the eBPF XDP model. As soon as the packet comes, you can run your eBPF program with the help of XDP hook in a device driver layer. There you can perform the load balancing logic. According to whatever action is being done and whatever decision is being made, you can either send traffic directly out of that device driver layer instead of sending it to the kernel networking stack if not required. You can directly bypass the packet to the user space, pod, or containers using AFXDP driver, or you can send traffic to kernel networking stack as well if some kernel processing is being required. And inside kernel networking stack, there are multiple eBPF hook present at certain points, like TC hook, socket hook. Then comes the VPP DPDK model. So as soon as traffic comes, with the help of kernel modules like VFIO PCI driver and with the help of DPDK provided poll mode driver, you can bypass the kernel networking stack layer and can send traffic directly to the user space where your load balancing logic will be running. Also, with the help of DPDK, you can use accelerator units provided by the specialized hardware like crypto, flow classifier, DMA. So you can also send traffic to your specialized hardware units where there are certain blocks or will be present to perform certain specific operations and to accelerate those operations. So we did some benchmarking. Now, there isn't any specific load balancer present that supports all the data planes that we discussed earlier. While these technologies can achieve line rate performance with proper setup and tuning, comparing different load balancers for different data planes with varying features will be like comparing apples and oranges. So that's why to address this in a cloud-native context, we choose Calico CNI, which supports multiple data planes. eBPF, VPP, IP tables are one of them. So we conducted some basic benchmarking. Now, Calico with VPP supports some 5-6 different primary network interfaces from which they claims that AFXDP gives the out-of-the-box performance, where other alternatives also give good performance but require complex setup. So that's why we used AFXDP with VPP, which gives good performance as well as easily integratable. The only thing you need is like the appropriate kernel version to run this. So this is how the numbers are. Now, VPP has the potential to perform better as it processes packet in burst. But AFXDP currently does not support burst packet processing features, hence it is these numbers, hence VPP performance is not up to the mark. If we move to network interfaces like, if we move to options like DPDK and other VPP native drivers, which have the ability to send packets in burst, then we'll see the enhanced performance in terms of VPP. So we are working on those different drivers that VPP supports, and that's still with our Octane processors, and that is still work in progress. But still, without any acceleration, VPP is able to show near performance number to eBPF, and in the UDP case is much higher.
Quick question, why is UDP so much comparatively small than TCP?
VPP UDP is faster than TCP actually.
It's 25809 and 24050.
Yeah, so the thing is that if the burst packet processing is there, then TCP will show more numbers.
So your question is why UDP is not much higher?
Yeah, my question is actually why is TCP so much faster than UDP?
No.
Because my thinking is that TCP is working at a much higher level,
Right.
and there's so much more processing happening in order and all of that stuff.
Right.
UDP should actually be a much faster.
Right. So I think it's about the files which are used in the exact test. Okay. So, yeah.
So yeah, in terms of CPU usage, VPP is showing the maximum numbers because of continuous polling. VPP has more CPU usage, and eBPF is showing the least numbers. And yeah, we did some WireGuard benchmark as well, and this is how the numbers are. So now we'll discuss in details the benefits and limitations of all these three data planes. eBPF first. So coming to the benefits, eBPF programs are very lightweight. That's why they offer low performance overhead. Minimal CPU and memory consumption is there. Then eBPF allow us to write custom eBPF programs that are tailored for specific needs. So that offers adaptability and flexibility. And then also eBPF programs allows us to use kernel resources and features instead of bypassing the kernel layer, which its alternatives are doing. Coming to the limitations, eBPF will not be good for CPU-intensive tasks like cryptographic operations. For decryption and decryption, you need to build a structure and do a lookup for each and every packet. For layer 7, if there are like several HTTP connections on a single TCP connection, eBPF will detect every packet and apply policy on per packet basis. And it also lacks support for offloading cryptographic tasks and hardware acceleration framework. And it also uses kernel libraries for performing encryption and decryption, not like the third-party operations which its alternative are using. Then comes VPP. VPP gives high performance because it processes packets in burst. With the appropriate driver, it gives high performance. Then VPP offloads cryptographic tasks to specialized hardware using DPDK cryptodev libraries, enabling better performance and hardware-based acceleration. And then VPP also have highly optimized implementation for a widely used tunneling protocol that is IPsec for secure networking. Coming to the limitations, VPP requires integrated setup and tuning, which can complicate the deployment in rapidly changing microservice architecture where your pods are getting deleted and created every second. Then comes memory consumption. So because VPP is using polling mode, memory consumption is little high. VPP manages its own memory and resources. And also, it's depend on directed graph architecture. That's why for adding or deleting new policies in a dynamic environment, we require to continuously realign the graph, which will be complex and time consuming. Then comes DPDK. So DPDK gives you high performance because of the use of pneumo optimization, which allows for better performance by ensuring that memory allocations are local to the processing cores. DPDK offers pole mode drivers. That means you can directly take packets from the interface. These drivers continuously poll network interfaces for the traffic and disabling the need for relying on interrupts. Then comes the multi-core scalability. So DPDK is designed to exploit multi-core architecture. It allows parallel processing across multiple cores, significantly increasing the performance. Coming to the limitations of DPDK, pods that use DPDK must run in privileged mode to access VFIO devices, raising security concerns by granting extensive permission to the containers. Now, if you give a NIC VF, if it has been passed to a pod as a device, then it will not be available for other pods on the same node, limiting the resource utilization and flexibility. And then comes to the dynamic scalability. So DPDK runs in old thread outside the kernel with a dedicated scheduler. So for every change, you need a full reset of the application. So after talking about all these three data planes, we will come to some futuristic data planes that are also programmable. So P4 programmable data planes. P4 is programming protocol independent packet processor, which is a domain-specific language for networking devices. It describes how the packets can be processed by the networking device. It allows custom packet processing on your hardware devices that are tailored for load balancing strategies and different algorithms. Now, there are no P4-based load balancer in production, but there are still some proposals and research offers like Sharon, ECMP, and server load balancer. P4 is a protocol-independent language. It allows dynamic reconfiguration of the hardware pipeline. It's highly programmable and good for rapid prototyping. And it supports some advanced features, and also it has a support for SDN, like an SDN-based controller. So coming to the benefits and trade-offs of P4, a P4-based load balancer runs in a programmable switch, so it eliminates the deployments of running an actual load balancer. Then a programmable ASIC-based implementation is faster and it supports dynamic configuration of the pipeline without a reboot. So without resetting and rebooting your hardware, you can change pipeline on the go. And then a P4-based load balancer can be installed on multiple programmable ASIC with minimum modification as long as it supports P4. Now, P4-based load balancer often require external controller to maintain session information and monitoring service health. So natively it doesn't support that. You need additional controllers, additional SDN controllers for that. Health checks in P4 are complex, requiring extra logic at L2 or controller level, which makes auto-scaling and group monitoring harder to implement. And then also P4 has the necessity of programmable hardware. So you cannot run P4 until your until your hardware is programmable. And those hardware are usually specialized, but very less support programmability. The hardware that are available now, they are mostly they are specialized for certain tasks, but lacking in programmability. So some key use cases in application of load balancing and how you can use these two according to the feature they support. So for microservice architecture, Kubernetes environment where pods are getting deleted, created every minute, every second, eBPF XDB, which is more programmable, will be a greater option. eBPF runs on different hooks that are inside the kernel at various places, so observability and monitoring would be, like eBPF will be good for that. Then for virtualized network function, high traffic web services, where you need high performance VPP, DPDK will be beneficial. When security is concerned, DPDK provided libraries for cryptographic operations, and drivers would be beneficial for secure networking application, edge computing solutions. So this is how, for various use cases, one technology excels whether other limits. Now we're talking about data plane and technologies. We will also talk about load balancing with specialized hardware unit. So these devices have been designed to accelerate specific workloads rather than do general purpose computing. So some of the examples are DPUs, that are data processing units, FPGAs, advanced or smart NICs, and ASICs. DPUs can be used, the DPUs combine the efficiency of custom hardware with the programmability of a software to deliver a high performance. FPGA can offer unparalleled flexibility and raw packet processing for load balancing tasks. SmartNICs with built-in load balancing support and traffic management features can drastically improve the overall system performance. And then there are ASICs that can be used, can be dedicatedly used for performing load balancing with some for having like high performance load balancers. So yeah, some of the advantages of using specialized hardware for your load balancing. They offers low latency. Dedicated hardware can process traffic and make load balancing decision much faster as compared to their software alternatives. Then offloading complex networking tasks to dedicated hardware frees up your CPU cycles on your server to perform some other critical operations. And then comes high density. More processing power can be packed into smaller areas. Specialized unit can handle massive volume of network traffic without any bottleneck or performance degradation. This efficiency not only reduces operational cost, but also minimizes the environmental impact on data centers, making them more suitable. And then they're optimized for specific workloads. So this optimization allows these units to handle tasks that would otherwise be inefficient on uh, general purpose processors. So yeah, some of the key takeaways. So we talked about the different data plane options that are there. They all have some benefits, but also some limitations. Now, growing security demands and increasing packet rates are like making us to re-evaluate what are the current data plane architecture we supports and whether they are fulfilling all the needs of the upcoming challenges. Then the future will require advanced security protocol, which will require complex cryptographic operation where specialized hardware accelerator will be a need. And as AI/ML application expands, network must provide real-time, high-performance, and secure data processing. So for that, we will be needing programmable data planes to meet the future requirements. So yeah, thank you. We can start with the Q&A. Also, we have Ravi Chandra here from Marvell, who has 14 plus years of experience with VPP and DPDK. So he can join for the Q&A.
Yeah, if anyone has any questions, we can go over them. Yes. Yeah, that is one of the limitations. But if you have L4 load balancing, or at L3, if you want to do load balancing based on, let's say, DSCP fields, like there are some algorithms like L3 DSR, okay, which operate at L3 level. So if the logic is not too complex, like you don't need to decrypt the payload and see what is inside and then take a decision. So for such use cases, eBPF based is what we are such. Actually, whatever we have shown here is with AFXDP and VPP combination. But with native drivers and DPDK drivers or plugin in VPP, it can be significantly higher. Okay, but currently there is no support for it. we are working on it, how it can be done. But coming to AFXDP with VPP, eBPF based is almost same, and in some cases better. Okay. So that's why with the current support and the integration capabilities, eBPF is the right choice for now.
Also, I think eBPF is supported by the kernel, right?
Right.
So that means that anything which a driver which has a kernel driver is well supported by eBPF.
So it's not, it's a hook actually, it's a XDP hook.
Yeah.
And you have to write eBPF code, and you have to compile it and load it.
Does it matter which DPU you use or which ASIC you use or to do TCP or IP offloading and all that sort of stuff? Does it really matter what is the underlying, you mentioned, right?
Right.
Yeah.
There are DPU that Marvell makes, and there are
Right.
other things, ASICs, and all these new ones are programmable
Right.
controllers, offloading, offloading. So does it matter what you are using to be able to use one of these?
For
For-
eBPF,
Yeah, for the eBPF at the XDP hook layer, at the driver level, we don't need any support for external hardware. But if we are doing some XDP offload, there are some proposals like HXDP, hardware-based XDP, then you need appropriate hardware for that.
the features supported by eBPF are very limited because the instructions are itself limited because kernel doesn't want to, you don't want to violate anything in the kernel space.
BPP and all, they will require much more specialized hardware, right? The vector processing.
Yes, yes, yes.
So it requires that specialized hardware to be there on that.
Right, right. As long as you have drivers for them supporting the standard frameworks, you can get best performance compared to even eBPF. That's what you're saying. Yeah, we have shown some numbers. These, okay. Maybe we can just go over them once. So, yeah, we did performance for pod to pod and pod to service communication. Throughput. These are throughput wise.
Can you show the next one, the CPU and the server, client CPU? There's not much difference between the client and the server. I mean, all of them roughly tax at both the sides equally.
Right, right, yeah.
There's nothing that the server is more, is less stressed or whatever.
Yeah, it's right now what we did is very basic IPEF, TCP test and UDP test. I think depending upon the protocol, I think it might
The
vary.
client and the server are the same CPU.
Yeah, they're on the same CPU, yeah.
They're the same.
Yeah,
Both are same x86 systems.
yeah.
Yeah, if you observe here, VPP has slight higher CPU usage because it operates in poll mode, and most of the time the threads are polling for the data.
So it's basically wasting CPU space.
Yeah, that's where it comes in, right? So it has capability to do more, but current feature which we are using, right, AFXDP, it is not giving enough workload for it. Yeah.
So most of the time it is idle, but just polling.
Right, right. So there is a metric in BPP where you can see what is the average vectors you get. I think that as per our test, it is very less. So it can even do more processing.
Have you tried dedicated hardware interfaces for comparison?
Yeah.
BPP requires dedicated hardware because if you compare without dedicated hardware, of course it will be slow because eBPF is very generic.
Right.
Have you tried?
No. So we are in the process of trying with the dedicated native drivers, right? That's what you are saying. Dedicated hardware with their native drivers in VPP. So we have native drivers for that. We are yet to do that performance comparison.
I mean, this is for the generic one, right?
Yes.
BPP will be slow, right? That's
Correct.
why telecom devices have dedicated interfaces for BPP.
Right. Yeah. So this is very. This is for whatever we have already. So we are in the process of doing it. I think we will see if we can produce them in the next session. Anyone else? VPP and DPDK and eBPF flexibility, you mean? Yeah, correct. So that is the limitation there. So if your logic is very simple, it's about just looking at some fields in the existing packet and make the decision. eBPF suits for such use cases. But if there is a use case where you have to decrypt the packet, just an example I'm giving, okay. So in such cases, eBPF doesn't provide a way to do that, okay, because it's very limited. The kind of instructions which are supported at the kernel space is very less. So for such use cases, DPDK suits better, or DPDK or VPP based, anything suits better. VPP and DPDK are kind of similar. Only thing is that VPP comes with extra features, as in like you already have a software stack which supports L2 to L4 processing.